All right, so now we're going to look at estimation and presence of hidden variables. Okay, and in order to start this discussion, we're going to first consider statistical models with hidden variables. Okay, so let's say we have a statistical manifold M, which consists of probability distributions, parameterized, it's like by parameters c. Okay, and then what's going to happen is that we're going to partition this random variable x into two parts, uh, one of which is observable and the other one isn't, right? So where the random variable sort of x is written as y comma h, right? So where y is observed and h is hidden. Okay, so hopefully that's understood, right? So you have a probability distribution which is defined. It's like on a bunch of random variables. It's like, but only some of them it's like you can observe. Okay, so the question is, can you estimate this parameter with only access it's like to the observed data, right? So the question is, can you estimate with just observations of y, right? So one very easy way to try to approach this is to look at the marginal distributions, right? So, so one can eliminate the hidden variables, right? By marginalization, right? Which is to say that you look at some py, which depends on y and c, and it's just given by the integral of p yh over h, basically, right? So if you do that, right, so now we have, right, a new statistical model, an induced statistical model. Let's call that M prime, right, which involved these sort of marginal distributions, right, which doesn't have any hidden variables, right? So that's sort of one very natural way to do it. Okay. So the problem is that sometimes, it's like the distributions in the original space with the hidden variables is nice, but these, it's like distributions, it's like which come from marginalization are complicated. Okay, so the problem is that in many cases, right, the form of P x c, right, is simple. An estimation is tractable in M. But when you look at the marginal distributions, the form is much more complicated. Because you have to do this integral over h or a sum over h, right? And then because of the fact that, well, because of the situation in some instances where this family of marginal distributions is complicated, then, it's like the estimation problem becomes intractable. Okay. So in particular, what oftentimes happens is that, it's like we've looked at situations where the exponential family plays a very, very clear role. It's like in the context of information geometry, it's nice. It's very, very easy to do estimation there. So usually what you would expect, well, not expect, it's like, but oftentimes what happens is that the original probability distribution with the hidden variables is an exponential family. Okay. So typically, right, M is an exponential family. And then we've already seen that when you have this exponential family, it's like a lot of times the estimation problem is easy to formulate. Okay, so so what is going to end up happening is that we're going to end up using it's like the EM algorithm, right, to to address this question of what happens. It's like when you have again a statistical model. It's like with hidden variables. Okay, then we will apply EM algorithm to address sort of estimation with hidden variables. Okay. All right. So, so that's sort of the high level. It's like a goal of what we're trying to achieve. So let's try to be more specific about how you go about doing this. Okay. So hopefully it's clear what we mean. It's like by hidden variables, these are just things which you don't observe in the data, right? Even though the probability distribution is defined, it's like on that as well. Okay, all right, so let's consider a larger model. Okay, so let's call it S, which is Q, which depends on Y and H. So, so basically now I'm not worrying about parameterizations, I'm looking at all probability distributions. It's like on the entire random variable space. So this consists of all probability density functions. On the random variables y and h. So let's say that when y and h are binary variables, right? S is a probability simplex. And we know that the probability simplices are an exponential family. And is an exponential family. Okay. So you can consider the case of continuous variables similarly. Okay. And then, but anyhow, all right. So so this model space. So the model space M, right, is included in S as a submanifold. Okay, so in essence, what's happening is that you have this space of this statistical model space which you're working with, right? And you're going to embed this. It's like in the space of all probability distributions, viewed as an exponential family in some sense. And then we're in this situation, basically where you have a curved, it's like submanifold. It's like of exponential families in essence. Okay, so that's how you're going to think of M as being an embedded. It's like family. It's like of curved, curved embedded family. It's like of exponential sort of distributions, if you will. Okay, so let's see what happens with the observations. Excuse me. So the observed data gives an observed point. Right. So let's call that Q bar of X is just, the average of these delta distributions. Okay, so this is just a term in the probability simplex. In S, where for now that we're assuming that S is fully observed, right? Right, so this is really nothing more than what's called the empirical distribution. Right, so if you take measurements, it's like from some distribution, you can construct, it's like, you can always construct this empirical distribution, which just comes from, it's like more or less assuming that, the observations you make are defining it's like a particular probability distribution, right? And that the more or less, how should I say it, that the drawn data, it's like what you have, the observations which you have exactly represents the distribution, right? So that's what the empirical distribution is. Obviously, it's an approximation, but that is still formally a point. It's like on the space of all probability densities on the random variables, right? So yeah. And so, as you might expect, one way to try to approach this is that you draw your data. It's like you construct an empirical distribution, which is in this sort of exponential family of all probability distributions, and then you do some sort of projection. It's like onto this statistical manifold M, in order to construct your estimator in some sense. Okay. So, all right. So when S is an exponential family, it is given by the sufficient statistic right? Eta bar is equal to x bar, which is just 1 over n, the sum of xi, okay, in eta coordinates. And then the maximal likelihood estimator, right, is given by m projecting, it's like this empirical distribution to m. Okay, all right. So the problem, of course, is that you don't have a fully observed point. It's like in the hidden variable case, right? So let's see what happens. So in the hidden variable case, we do not have a fully observed point by definition, right? So we only observe the y components. So what happens in essence is that you can still construct an empirical distribution, but it's an empirical distribution which is associated with the marginal, right? So we have an empirical distribution let's call that q bar y, right, which depends on y. So what we want to do is that we have to essentially do the following. In essence, it's like what you're doing, if you will, is that you're using sort of Bayes' rule here, right? So in order to have a candidate for a joint distribution. Let's call that, Q bar, which depends on both y and h, right? We basically use an arbitrary conditional distribution Q of h, it's like conditioned on y, right? And then sort of apply Bayes' rule, which says that Q bar y of h, right, is equal to this marginal distribution times this conditional probability. Okay. Okay. So you might immediately object, it's like, which is to say, it's like, well, how do you go about choosing, it's like this conditional probability Q of h conditioned on y, right? And so when in doubt, it's like, you have no reason to prefer one of these conditional probability distributions or another, so we're going to consider all of them, right? So since Q h conditioned on y, right, is arbitrary, right, we take all of them as possible candidates. Of observed points. And consider the following submanifold. Okay, so this is D. So it's the set of joint probability distributions where this joint probability distribution has the form, this empirical marginal distribution times an arbitrary conditional probability, and then this conditional probability is arbitrary, right? So what's that basically saying is that, all right, you've made an observation, right, which is the which is an empirical distribution, but it's like only in the observed variables, right? So you're basically trying to then look at all possible joint probability distributions on the entire random variable space, including the hidden variables, which are compatible with that empirical distribution. It's like, which is an approximation of the marginal distribution. And the way you do this is by sort of looking at allowing, it's like, this particular conditional distribution to vary. So that's the, in some sense, that is the sub-manifold, it's like, of observations, it's like, which are compatible with the empirical marginal distribution. Okay. Okay, so this is the observed submanifold. In S, which is specified by the partially observed data. Y1 to Yn, right? So that's, so that's not so surprising. It's like more or less, it's like what's basically happening is that if you have, it's like a fully observed point, you can construct an empirical distribution, which is just a specific probability distribution in the space you're working with. Okay, because of the fact that you haven't observed, it's like all the possible data, you can't actually construct a single point estimate, right, of which is an empirical distribution. So the empirical distribution which you get of just coming from all these observable data is consistent. It's like with a set of points on the statistical model space. Okay, and so I've written it's like this set of it's like probability distributions which are compatible with this empirical distribution in the following way here. Okay. So, all right. So now it's like I'm going to use the specific form, it's like of the empirical distribution, right, to characterize this set. So by using the empirical distribution, as my Q bar, a Y, right, you get that QYH is 1 over n, the sum of the deltas, the direct deltas y minus yi, times QH conditioned on the yi's. Okay, so this submanifold D, okay, is M flat because it's linear with respect to this conditional probability. Okay. All right. So that's sort of the general abstract setting. And then what we're going to do next is to look at two examples. It's like of things which fit into this setting. And then we'll talk about how do you actually use the EM algorithm to address this estimation problem. It's like when you have hidden variables in this kind of setting. All right. So let me just stop here for now.